inviting me to this conference. I think it's kind of appropriate that I showed up in the snow and then heard these words about how Fort Collins is a nice place to live. You know, when I give this kind of talk in the U.S., I often show a map that has sort of average temperatures and cities like Fort Collins moving south, you know, as the climate changes. Sadly, even though I tried, I couldn't put anything together like that for Calgary, so I can't tell you exactly what's going to happen here, but neither can anybody else. But I do imagine that in a generation's time, things will be different here. So I want to start by talking about the difference between weather and climate, because you know, I'm flying here in a snowstorm to talk about global warming. And I got an email this morning that said that it was going to be something like 15 degrees tomorrow, so much, much warmer than today. So, you know, many of us have heard a sort of a sniping comment, if they can't predict the weather, you know, next week, how the heck can we believe what they say about the climate in 100 years? But there's a difference between weather and climate. And where I come from, everybody knows how to answer this question. If you don't like the weather, you know, wait 5 minutes. And I suspect that it's fairly similar here in Calgary as it is in Denver or Fort Collins. But if you don't like the climate, you're out of luck. You know, if you don't like the climate, there's not a lot that you can do short of moving. Because climate is place. Climate is place. And we know places. We're familiar with places. I grew up in New England, in a place of forests and sort of pastoral landscapes and towns that wind along rivers. None of the streets are straight or at right angles. And I moved 30 years ago to the high plains where everything's sort of laid out in a grid and looks like it's all been built since World War II, because it was. You know in your bones that it's different here than it is in Arizona or Brazil, and that these places are not changing the weather. You don't change Brazil into Calgary, you know, from one day to the next. The weather changes 1 minute to the next, but the climate doesn't. Climate depends on where you live. Climate depends first and foremost on latitude, and you know this. Climate, especially around here, you know that climate also depends on altitude. The climate here is different than the climate in Banff. The climate in Fort Collins is different than the climate in Vail. Climate depends on what's upwind. If you've ever been to Vancouver in the middle of the winter, you know, it's gray, it's drizzly, it's kind of not so pleasant necessarily, but the grass is green. But if you go to Montreal, which is also at sea level and it's also at the same latitude, the grass is not green in Montreal in January. In fact, you'd be lucky to see the grass in Montreal in January, because what's upwind of Vancouver is the great big blue wet thing, and what's upwind of Ottawa or Montreal is the rest of Canada. So what's upwind matters as well. Climate changes very slowly. Climate, you know, where you live changes, but it changes slowly. It's not like the weather. And believe it or not, climate is very predictable. I can predict reliably that Ecuador is warmer than Edmonton. And it's for the same reason that I can predict that the future will be warmer than the past. The real reason has to do with heat budgets, with heat in and heat out. Did you ever wonder why day is warmer than night? Probably not. You know, figured that out as a little kid. Why summer is warmer than winter, why Ecuador is warmer than Edmonton. It comes down to heat in and heat out. If you put more heat in than you take out, it gets warmer. If you take more heat out than goes in, it gets colder. Now, the fact that it's cold today and it'll be warm tomorrow, that has to do with heat in and out of the sides. We're going to have some warmer air blow in here tomorrow, and the weather will be different. But when we talk about the climate of the Earth, there aren't any sides. The Earth is round. The Earth is round. You can move this stuff around from side to side all you want, but the total amount of heat in the Earth doesn't change. The only way the climate of the Earth can change is if you change the heat going in and out of the top. There aren't any sides. All of the heat that comes into the Earth that warms us up comes from the sun. But if that was the whole story, the Earth would just get hotter and hotter and hotter and hotter, right? Heat in minus heat out. But there is heat out of the top. In fact, the heat goes out the top through radiation. You can't see it, but you can feel it. And you may wonder whether you even believe in such a thing, that you can't see, but that somehow affects your life and controls the climate. But if you've ever used an electric range in the kitchen, you know, you turn on one of those burners and you can feel the heat coming out of the burner before you can see the burner glow red. And that's thermal radiation. You emit it, I emit it. Most of what we feel as temperature in this room, in any room, is actually an exchange of heat in and out of our bodies. We radiate out at something like 600 watts. But the world, the walls, the people around you, the table are radiating back in at 600 watts. And if more comes in than goes out, you warm up and you take off your sweater or vice versa. So the Earth works this way too. The Earth has to get rid of heat at the same rate that it takes in heat. The sun shines in, the Earth shines back out in the thermal part of the radiative spectrum that we can't see. So I want to talk a little bit about carbon, which thank you to the introduction. That's actually what I study in my other life as a researcher. Carbon is an amazing thing. Carbon is made in stars. Carbon is the element on which biochemistry and life is built. Plants do a remarkable thing. It's nothing short of miraculous, really. Plants take carbon atoms, which are bonded to oxygen in the atmosphere, just dead, inert CO2 gas, inorganic molecules of air. And they use the energy of the sun to string those atoms together into more complex molecules, carbohydrates and biological molecules, at which point they're alive. It's an incredible thing. Non-living air transformed into living material by the magic of photosynthesis. This is how the entire ecosystem food chain is based, on solar energy harvested by plants. Now, nearly all of that energy is then harvested by the living things to run their biological processes. I'm up here waving my arms, jumping up and down. Has to do with breakfast, has to do with the cinnamon rolls out here in the hallway. But where did the energy in the cinnamon rolls come from? Well, it came from plants. Ultimately, it came from the sun. So my biological energy, the energy through which I can stand up here and hold forth, was derived from plants. And almost all of the energy in the Earth system is harvested in this way by photosynthesis, and then it's released back to CO2. When I burn the cinnamon roll, I breathe, and the CO2 goes back out into the air. So there's this flow of carbon in and out of the living things, which is the flow of energy in the system. There's a little bit that's left over, of course, as fossils, literally fossils. Dead stuff that didn't get a chance to decompose can accumulate in the soil, in the bottom of the lake, in the bottom of the ocean, and over time it gets buried. And you can see here a dinosaur walking around on the ground as the buried fossils decompose in the deep rock, and eventually some of that stuff floats, literally like olive oil on vinegar. This is petroleum floating on water until it reaches, a layer of rock that is impervious and doesn't allow it to get up. And then sometime later, the dinosaur is replaced by a pickup truck here as people drill little 7-inch diameter holes down into the rocks and extract the fossils. And of course, that's what we use to run our entire global economy, is the energy that was harvested by plants, which somehow escaped being decomposed by microbes and is now being burned to drive the entire global economy. So we dig this stuff up. There's the hydrocarbon molecule at the top, all those strung together carbon atoms that were transformed from non-living air into living things and are now hydrocarbons in the ground. We put it in our engines, we put it in our power plants, we transform it back in the bottom there into carbon dioxide, CO2, and water vapor, H2O, and then those little lightning bolts indicate the energy that was stored in those carbon-to-carbon bonds, and of course that's how we run the world. Here's some carbon that was brought up from the ground. And it's old fossil carbon now being harvested for energy, the carbon being injected back into the atmosphere. This has happened before. We want to look at climate in the larger context of geologic time, of climate changes in the past. And as you probably know, there was a time about 18,000 years ago when much of the land in the northern hemisphere was buried in ice. It's called the Ice Age, but it's actually just the most recent of a series of about 20 such ice ages. Over the last couple of million years, the ice has grown and then melted back and grown and then melted back sort of every 100,000 years or so. And the most recent maximum extent of the ice was about 18,000 years ago. Not that long geologically. I mean, there were people around then. There were human beings that were coexisting with wildlife and ecosystems along the margin of the ice 18,000 years ago. The ice was all through the Rockies, though not down in the prairie. And on the eastern part of North America reached all the way down through the Great Lakes to Chicago and New York. Of course, there was no Chicago and New York then. But what we find is that when we drill holes down through the ice that's left over, there are tiny little bubbles in those ice cores, and the little bubbles are literally fossil air. So you go to Antarctica. I've never been to Antarctica, but I've seen these ice cores that have been brought back from Antarctica. I saw them in a lab in Melbourne, Australia, on a summer day, sweltering heat. I don't know if you've been to Australia. I like to think of it as Brits in Birkenstocks. You have to put on a big parka and you go into this super duper freezer that's minus 40 in there, and they've got this priceless ice that's been brought back from the ice sheets in Antarctica. You slice the drilled cores into thin little slivers, and you can actually extract those bubbles. Where did the bubbles come from? They were actually air that was trapped between snowflakes as the snowflakes accumulated over millennia. And the compression of that snow trapped the air and made little tiny bubbles. We can take the bubbles and run the air from the bubbles through scientific instruments, measure the amount of CO2 in the bubbles, and we find that, remarkably, the CO2 in the atmosphere has gone up and down and up and down and up and down as the ice has grown and shrunk and grown and shrunk over hundreds of thousands of years. These cores, this particular data that I'm showing here, goes back through 4 cycles of ice ages where it's marked ice, and then interglacial periods like today where there's very little ice. And the CO2 is higher during the interglacial periods and lower during the glacial periods. It's remarkable. It's actually beats like a rhythm. As the ice grows and shrinks and grows and shrinks, the amount of CO2 in the atmosphere grows and shrinks with it. The CO2 changes didn't cause the ice ages. Rather, the ice ages caused the CO2 to change. But it's almost like a thermostat. When the ice comes, the CO2 is extracted from the atmosphere, probably dissolved into the oceans. And the CO2 goes down to about 180 parts per million, 180 molecules of CO2 per million molecules of air. Then when the ice melts, the CO2 comes back into the atmosphere, but it stops at about 280 parts per million. So about a third of the CO2 goes out of the atmosphere and back in as the ice comes and goes and comes and goes. This wasn't known until the 1990s, until we got these bubbles back from Antarctica. And it's still somewhat contentious as to how the heck this works. You know, what is it that makes the CO2 stop going away at 180, and what makes it stop coming back at 280, and so forth. But if we look today, we're at roughly 400 parts per million, 400 molecules of CO2 per million molecules of air. And you can see that compared to the ice ages. It's the same data here, but now I've included the modern measurements, the measurements made at Mauna Loa in Hawaii since the 50s, that show this huge spike. So the CO2 has increased in the last 100 years as much as it did coming out of the last ice age. It's a remarkable thing. Of course, even still, that's only about a third. So we went from 300 to 400 parts per million, so about 1/3 increase in the CO2 over the last 100 years. But basically, you ain't seen nothing yet, because if China and India continue with Plan A, which is to build modern economies for billions of people using coal as the primary source of energy, we won't see a 30% increase in this century. We'll see a 300% increase in this century. So we go from 180 during the ice ages to 280 in between the ice ages to 400 today to 1,200 ppm, 1,200 parts per million by the end of the century. It's an enormous change, much, much bigger change than has happened during the glacial and interglacial cycles of the past. I need to talk a little bit about why this is important, why this matters. And I understand this isn't a science conference, it's a literary conference, but I'm going to get all sciencey on you for 2 slides here. I promise not to belabor this. But I want you to imagine the energy that's flowed into the Earth system from the sun, and imagine that it's radiating back out. Just as I told you, you radiate, and the tables radiate, and the burner on the stove radiates, so also does the Earth radiate heat back to space. And as that radiation streams back out into space, it encounters molecules of air. You've never seen a molecule. You may not believe they exist. If you don't believe me, ask your pharmacist. Molecules are everything. Everything's made of molecules. 99% of the molecules in our atmosphere are made of 2 gases only, oxygen and nitrogen. That top one is supposed to be O2, and the bottom one is N2. Oxygen and nitrogen, 99% of the molecules in our air, and they're made of 2 atoms of the same element. So you've probably somewhere in your education heard about the atoms have positive charges in the middle and clouds of negative charges that run around, and the negative charges are shared between the 2 positively charged nuclei, and that's called a bond, a chemical bond. So we have doubly bonded oxygen on the top and triply bonded nitrogen on the bottom. And as those electromagnetic waves go up through the atmosphere, carrying the heat back out to space, the oscillations of electric fields and magnetic fields, which constitute the radiative cooling of the Earth, encounter these clouds of negatively charged electrons, and the magnetic fields get the electrons sort of sloshing back and forth. And you can imagine that as a vibration in the molecule. The energy is actually absorbed by the molecule, and it causes the molecule to vibrate. So think of it as kind of ringing. Ooh. They don't actually make that noise. I made that part up. But the energy is no longer streaming out to space. It's absorbed into that vibrating molecule. And then the molecule can unvibrate, if you will, or de-excite, releasing the energy back out, up, down, sideways, whatever. If it goes up, it cools the Earth. If it comes down, it warms the Earth. But you can imagine it going, woo, whoa, 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 back down to its ground state. And 99% of the molecules in our atmosphere have only this one mode of vibration, getting longer and shorter along the shared electrons. But CO2, carbon dioxide, is different, as is water vapor. That's the one on the bottom. The difference here, less than 1% of the molecules have this character, but they're very important, because these molecules have 3 atoms instead of 2. Carbon dioxide is a greenhouse gas not because capitalism is evil, not because greed is bad, but because it has 3 atoms. It's just bad luck. CO2 can do the same thing that O2 and N2 can do, only now I only got 2 hands. I'll make this one, my head will be the carbon, and each of these will be an oxygen. Just like O2 and N2, CO2 can go whoa, 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 whoa. But there's more. It can go boom, 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 beep, boom, 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 boom. So each of these different ways of wiggling will absorb a different wavelength of energy. Each of these different molecular vibrations interacts with a different color, if you will, a different kind of thermal radiation that's going out. And that's what makes CO2 good at absorbing heat. It's also what makes it good at emitting heat, because as it de-excites, it emits this heat back out. H2O is actually even better. You've probably heard that. Water vapor is a great greenhouse gas because it's bent. It's got this angle in it, so it can kind of do this and this and this. It can even do flips, but I better not try that here. These molecules are responsible for about 2/3 of the energy received at the Earth's surface that comes in. For example, at night there's no sun, but it doesn't get infinitely cold at night. And that's a good thing, right? I mean, we would be very unhappy if it got as cold here as it does on the moon at night. The moon has no atmosphere. The Earth has an atmosphere. 2/3 of the watts, 2/3 of the energy that's received at the surface of the Earth comes from the warm sky rather than from the sun. This is conference is called Under Western Skies. I suppose I could call it Under Warm Skies instead. And it's the warm sky radiating this heat down that keeps the Earth tolerably warm, keeps the Earth habitable. If it weren't for these extra heat rays coming from the CO2 molecules, the Earth would be frozen solid. The oceans would be frozen to the bottom. It would be a white snowball floating in space, forever sterile. We're very, very fortunate to be here, and we owe quite a debt to these special molecules that can emit this heat and keep us toasty warm. So you've seen this picture before. The sun beats down on the Earth. Part of it reflects back off. Particularly the white snowy parts reflect really well. And then the red shows the thermal radiation going back out, some of that getting stuck with the heat, the special absorbing molecules and re-radiated back down, keeping us toasty warm. So I want to talk a little bit about how the greenhouse effect works in terms of common sense. Many of you are old enough to remember what this thing is. This is an incandescent light bulb. In particular, this is a 4-watt light bulb.
Back when I was a boy, we used them for Christmas trees.
You know, when my kids were little, we used them for night lights in the hallway so they could find the bathroom. But 4 watts. And if you double the number of these heat-emitting molecules up in the sky, this is how much heat you would add to every square meter of the surface of the Earth. 4 watts per square meter. So there's, give or take 2 square meters on this table, and I would have 2 little 4-watt light bulbs on there. But it wouldn't just be the table worth of square meters, it would be every square meter of the Earth, and those light bulbs would stay on 24 hours a day, 7 days a week, forever, at least for the rest of your life. And that would make the surface warmer. Of course it would. This is the science of global warming. This is the nugget, which is so simple, so easy to understand, that I'm flabbergasted at how much complexity we are presented about climate change in the popular culture, when really it comes down to this, that if you add heat to things, they warm up. This is a remarkably simple physical principle. Believe it or not, this business about 4 watts per square meter, about the absorption and emission of heat by CO2 molecules, was known long before light bulbs were invented. This fellow, John Tyndall, discovered the absorption and emission of heat by CO2 in 1863, 150 years ago, the details of the absorption and emission of heat by CO2 gas was well established. It's not quantum physics, it's not relativity. This is sort of science of the age of steam engines and the Industrial Revolution. So this brings me to common myth number one about climate change. People are worried about climate change because it's been getting warmer lately. Well, it has been getting warmer lately. You know, most climate change talks start with a graph that looks like this. This shows thermometer records starting in the 1860s, and you can see that it was kind of, the temperature was hanging in there during the 19th century, and then it went up for a bit in the early 20th century, and then it flattened out in the middle of the 20th century, and it's been going up since. And you see that someone has rather suggestively put yellow and orange lines on here, and you get the impression that, that this is where the concern comes from, is that, oh my, it's been warming up, and if it keeps doing this, we're going to be in big trouble. Well, that's not it. That's not why we're concerned about global warming. We're concerned because we know that when you add heat to things, they warm up. This is actually a principle in physics known as the first law of thermodynamics, but I swear you'd have to be some sort of egotistical Brit to call something like that the first law of thermodynamics. When you know, for God's sakes, cavemen knew this, right? You put the slab of mammoth on the campfire and it gets hot. Long before it was called the first law of thermodynamics, it was called the law of hot. And this is the basis for our understanding of global warming. There's no question that CO2 emits heat. This is a laboratory measurement that goes back 150 years. Really, the question is, if you add heat to things, do they warm up? Well, of course they do. So the more heat we add to the surface of the Earth, the more it will warm up. I want to introduce another sort of common misconception here, and unfortunately there's math on here, but it's easy math. What it says, it's named after a fellow named Kaya. 4 factors determine the future emissions of CO2. And it's possible to sort of express future emissions in terms of multiplying these 4 things. The population, that's the P at the end of that equation, times the economic activity per person. So think of it as like dollars of GDP per person, times the energy efficiency of that economy. So think of this as you know, joules of energy per dollar of GDP, times the carbon efficiency of that energy. So think of this as like tons of carbon per joule. You multiply those 4 things together and you get CO2 emissions. So the thing that's I mean, that part's easy. That's why it's called an identity. This is not really controversial. It's a definition. The thing that's really surprising is that population is not the driver of future climate. I run into this a lot. I give public talks about climate change, and almost invariably somebody says, well, isn't it really the problem is us? The problem is the people. The problem is there are too many people in the world, or we're reproducing too quickly. These 3 graphs show population demographic projections that are published by the United Nations. The bottom curve there, and they're all normalized to the year 2000. So the year 2000 equals 1, and the bottom curve there shows the expected changes in population of the world in the 21st century. And you can see that if it starts at 1 at the beginning of the 21st century, by the end of the 21st century, it's 1.4. So we expect a 40% growth in the world population in this century. The top line shows the projected gross domestic product of the world, gross world product, the size of the world economy. Population is expected to grow 40% in this century, and the world economy is expected to grow 1,600% in this century. And that's not even a particularly high rate of growth. That's a 2.8% annual growth rate. You know, and when the annual growth rate is below 2%, we throw the bums out. We replace our governments. If the world's economy grows at 3% a year, we expect something like 16-fold growth in this century. The middle line there is GDP per capita, so it's dollars per person. Now, this is a controversial thing that I'm saying here. I'm saying that the thing that's driving CO2 up, the thing that's driving climate to change, is not the fact that there are a lot of people on the planet. It's that those people are no longer going to be in dire poverty. It's actually a good thing, right? We want billions of people to emerge from dire poverty, from starvation, from privation. The trouble is, if they do it the same way that we run our economy now, the emissions will increase by 1,600%. That would be a real problem for us. Just FYI, I went last March to Shanghai, China, for work. It's sort of ironic. I was attending a global warming conference, so I had to burn enormous amounts of fossil fuel to fly to the other side of the planet. This is a photograph of an interesting place that I visited in Shanghai. It's called the Bund. I believe it's a German word. It's the big bend in the river there, and really interesting, cool neighborhood right there on the near side of the river in this photograph. It's all sort of European colonial architecture, late 19th century. You walk through there, you'd think you were in Germany or France. It's very familiar to those to people who've spent any time in Europe. There's a clock tower there, kind of on the right side of the photograph, and I thought it looked awfully familiar, but then it was 1 p.m. when I walked by, and it did its chime thing, but instead of like Big Ben, it had these Chinese intervals, sort of Chinese music. It was really cool. This picture was taken in 1990. I didn't take it, obviously. This is the exact same place in 2012. So let me just sort of A-B those for you. This is 22 years apart. Oh, there's no back on this thing. Uh-oh. I thought I could go back. Oh, I can. It's just slow. Okay, here's Shanghai 1990. Here's Shanghai 2012. Same spot, same picture, same place. Shanghai is an amazing place. The city proper has a population of 22 million. We visited a bunch of schools in the suburbs. Each suburb has population over 10 million. There are about 350, well, let me just stick with what I know. There are 300 million people in the United States. There are 10 times that many people in China and India put together. Those people are already here. They're already on our planet. And the vast majority of them are very, very poor. But they don't intend to stay that way, and you can't really blame them. And to try to solve our problem by reducing population by a factor of 10 is almost unthinkable. It's genocidal. It's dreadful. On the other hand, expecting all of us to live very, very poorly is also unthinkable. Or telling billions of people on the other side of the planet that they must remain poor so that I can continue to enjoy the lifestyle to which I've become accustomed just doesn't ring well in my ears. How much warmer are we talking about? The answer is it depends. Obviously 4 watts isn't a heck of a lot. If I put 4-watt light bulbs on every square meter in this room, and then beyond the room to the entire planet, how much warmer would it get? First off, it depends on how much CO2 we put in the air. So here we have maps of how much warmer for a low emissions, a medium emissions, and a high emissions world from the IPCC. And I want you to notice that the maps are not all one color. The maps have different colors, which show how much warming to expect by the end of this century. And the different colors are different warming. So one thing to notice right off is that the land gets a lot warmer than the ocean. And that actually makes quite a bit of sense. The oceans are very deep. On the average, the oceans are 4,000 meters deep. It takes a heck of a lot of watts to change the temperature of 4,000 meters of water. So the oceans stay roughly the same temperature. whereas the land warms up. So if it's going to warm, say, 3 degrees Celsius, and the oceans aren't going to warm, that means the land is going to warm much more than 3 degrees Celsius to make the average 3 degrees. The other thing to look at, just quick off the bat, is that the northern hemisphere warms much more than the southern hemisphere. And that's also, obviously, the land is mostly in the northern hemisphere, and the ocean is mostly in the southern hemisphere. So it takes a lot more heat to warm the southern hemisphere than the northern. The last thing to look at on that graph is that, or on the maps, is that the places with ice and snow on them warm much more than the places that don't have ice and snow. And that's because ice and snow are very bright and they reflect the sun's space and cool things off. And if you melt the ice and snow, then you replace a bright thing with a dark thing and it soaks up lots of sun. Think of asphalt parking lots on a July afternoon. And so that warms up even more. So if you happen to live on land in the northern hemisphere where it snows, you get extra. You don't just get the regular global amount of warming, you get somewhat more. In fact, if you look sort of in the middle of North America where we are, the low emissions world is about 3 degrees of warming and the high emissions world is about 6 degrees of warming, and that's actually quite a lot. This really isn't about polar bears, this is really more about agriculture and economy and rainfall and water supply, perhaps mass migrations. You have a ski industry here. It depends on snow. You have water that is brought to your cities and to your farms from melting snow. And if you change the temperature by 6 degrees on the average, you're moving Calgary to Denver. Your snow is going to be different. I have not seen your mountain pine beetle, but I have seen ours, and they're related. There's an incredible infestation of these little bugs that the ground zero is sort of the middle of British Columbia, and there's a sort of peninsula of them that reaches all the way down to where I live. They're the size of a grain of rice. You can see the tweezers there to show the size of the little bugs, but they kill forests. There are huge areas where I live that are 90% dead due to the mountain pine beetle. And the one reason why the pine beetle has done so incredibly well recently is that the winters are no longer cold enough for long enough for the cold to penetrate deep into the tree where these larvae winter over, and so they've been able to reproduce year after year and take over. We had devastating wildfires this year in Colorado. Several dear friends of mine lost their homes. It's a scary thing when the forest burns and the sky turns brown. And my mother actually died about a month ago from respiratory illness. But last summer, when the fires were raging, it was just miserable. She had to keep the windows all shut all summer and hang out in her house because the smoke outside was so bad. The acreage of forest that burns each year has doubled in the United States, in the western United States, in 30 years. Doubled the acreage of fires. Now, some of that is mismanagement. Some of that is down to forest management. Some of it is also due to greater evaporation into warmer air, to a greater evaporative demand that puts a stress on our forests and makes them much more susceptible to wildfires. Our agriculture is almost entirely irrigated in the part of the world where I live. I believe you're a little less dependent on irrigation here than we are because it's somewhat cooler and less evaporative demand. But still, irrigation is a huge part of the economy in our part of the world, and we would miss it if twice as much water evaporated. The U.S. is in a historic drought. It's more extensive than the 1930s. It's a remarkable thing to see these changes in our lifetimes. But I'm actually here to talk about the third millennium and somewhat beyond our lifetimes. One of the really remarkable things about climate change has been the dramatic transformation of the Arctic. In the last 30 years, half of the area of the polar ice at the end of the summer has disappeared. Let me say it a different way, make it a little easier. The North Polar ice covers half as much area as it did when I was in college. It's just astonishing. And the decrease in ice-covered area up there is dramatically faster than has been predicted by climate models. This is happening very, very quickly. It could be that within another 20 years, there will be no ice at all in the Arctic in the middle of the summer, or at the end of the summer, excuse me. I want to talk about where the CO2 goes, because this is misunderstood. This is almost nobody seems to get this. We talk about climate change in terms of emissions, but really climate change is about concentration. And I know this is sort of a subtle point, but think of it like this. Think of the atmosphere as a big bathtub, and it contains a certain amount of carbon. In fact, the units that I'm using here are a little bizarre. They're gigatons, you know, like gigabytes or giga something else. Giga is a billion. A gigaton is a billion tons. How much is a billion tons? Picture a cube that's 1 kilometer on a side, 1 kilometer wide, 1 kilometer long, 1 kilometer deep. If you fill that box with water, it weighs precisely a billion tons, okay? There's 800 times that much carbon in the atmosphere, which is the CO2. And the global economy is like the faucet at the top of the tub. This slide is getting old. You can sort of date my slides based on the numbers here. The slide says that 8 billion tons of carbon go into the tub every year. The real number now is 10. We've grown from 8 billion tons a year to 10 billion tons a year going into the tub. There's 800 billion tons in the tub. Lucky for us, in some ways, the oceans are dissolving some of that. About 2 billion tons a year goes down the drain into the oceans. Another 2 billion tons a year goes down the drain into the land. That's actually the subject of my research. Gosh, don't have time to really go into that, but what it means is that, believe it or not, as a planet, things are growing faster than they're dying. There's actually more and more and more living stuff on the planet every year to the tune of 2 billion tons a year. So between the oceans and the land, about 4 billion tons a year go out the drain. So we're running the tap. 10 billion tons a year goes in the tub. 4 billion tons a year goes out of the tub. Boop, 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 boop. The level in the tub goes up. The trouble is that the extra heat that we put into the Earth system comes from the water in the tub, not from the faucet. If you turn the faucet off, there's still water in the tub. If you turn the faucet down just a little, the water is still rising in the tub. You have to turn the faucet down further than the drains are taking it in order for the level in the tub to start going down. Pretty simple, but remarkably poorly understood. Where do these drains go? Think about that for a minute. There are 3 drains. I only showed you 2 because the third one is a teeny tiny drip. But the 2 biggest drains are into the plants, which I told you is a remarkable thing. I mean, everybody knows that plants take up CO2, right? I told you that the miracle of photosynthesis means that dead air turns into living things. But living things die. How long does the carbon stay in living things? Well, it depends. You know, if it goes into a giant sequoia tree, it might stay in there for a long time, maybe thousands of years. But if it goes into a blade of grass in my backyard, it doesn't stay very long, you know, just until the dog digs it up. But the fact that there's water going down that drain, the fact that there's carbon being taken out of the atmosphere by the biosphere means that things are literally growing faster than they're dying. There's a net increase in the amount of living things on the planet. And that's very difficult to sustain beyond a decade or 2. I mean, there's a lot of places you can't grow new plants, like the Sahara, like Greenland. You know, these places are just not gonna hold a lot of carbon. So we think that drain is connected to a septic tank, if you will, that's too small. That drain ain't going nowhere. That drain is going to fill up and plug up very, very soon. The second drain is going into the oceans. And the oceans are a handy place to put the extra CO2 because they're vast. There's an enormous, enormous reservoir of carbon dissolved into the oceans. Unfortunately, chemically, it's acidic, and it's bad for coral. It's bad for anything that makes its shells out of calcium carbonate. It's perhaps a worse problem than global warming in the long run. But you know what they say, in the long run, we're all dead. Nevertheless, it's actually remarkably difficult to get the carbon in the oceans to go down to the bottom. And I have to sort of ask you to believe something you haven't seen again, which is that the oceans, vast as they are almost entirely hidden from the atmosphere. So picture, I don't know if you've ever vacationed in the tropics, some lovely beach, and out there's the waves, there's the palm trees, there's the lovely beach lapping at your feet, but at depth, the ocean is bitter cold and pitch black dark. It's that cold water that forms up in the Arctic and the Antarctic actually sinks like a rock because it's so cold and heavy, and it just lays there at the bottom of the ocean. It's very difficult to get the surface of the ocean to get down there and mix with the deep part of the bottom of the ocean, and so it takes about 1,000 years to sort of stir the oceans, to get that cold water to come up and react with the atmosphere and then get back down there. In the long run, when both of these drains are plugged, where the carbon has to go is into the sediments and the rocks. And it will go there, whence it came. You know, we've mined the rocks and turned it into air, and eventually, in geologic time, it will return to rocks. But that will take millions of years, and that's a long time. We don't think in terms of those kinds of timescales. We're quite happy that these two big drains are draining away now, but we're still running the tap much, much faster than those two drains. And if we're depending on that last little drip going in the third tank, we're going to be in trouble. So this brings me to common myth number 2. When we reduce or stop burning fossil fuel, the CO2 will go away and things will go back to normal. And I'm so sorry to tell you that it's not true. The graphs here are not predictions. They're just illustrative. They're what ifs. So I want to start with the bottom graph there. The bottom graph starts, it shows the emissions of carbon in billions of tons, gigatons per year. I told you we're at 10 now. Starting in the year 1800 and running through the year 2012, there it says you are here. We're at 10 billion tons a year. If China and India build modern economies with coal, as we fully expect them to, the global emissions, that's the tap, that's the faucet into the tub, will reach 30 billion tons a year by the end of the century. And then let's just suppose that in the year 2100, somebody invents something, I don't know, dilithium crystals, and they shut off the tap completely. So over the course of the 22nd century, we run the emissions all the way from 30 billion tons a year down to 0. What happens to the CO2 is illustrated above in blue. You can see that the CO2, you are here at 400 parts per million. Following this scenario, the CO2 goes up to about 12 or 1,300 parts per million by the end of the century. And then when we turn off the tap, the drains progressively remove the CO2 from the atmosphere. But they're terribly slow, because by that time we've put so much into the tub that the drains just barely get rid of a little bit of CO2. And by the year, what is that, 2300, halfway between Captain Kirk and Jean-Luc Picard, we still have 1,000 ppm of CO2 in the atmosphere, and the temperature hasn't gone down at all. What we are doing is cranking the thermostat in a one-way system. A thermostat has a ratchet on it, and when we turn it up, it doesn't ever come down. This is a problem. This is a big problem, and it's not just a problem for the next election or the next generation. It's a problem that has legs, that really, really has long legs. In fact, you can run this kind of what-if scenario out for thousands of years. This graph shows the same calculation starting in the year 0 AD. The CO2 in the atmosphere at the Industrial Revolution, about 280 parts per million. You are here at 400. If we do the China and India coal scenario, we have this immediate, incredible spike in this generation, or next generation, and then thousands of years of very, very slow mixing with the deep ocean to get rid of it. It's an incredibly long-lived problem. So I want to talk a little bit about what that does to sea level, because this is a strange thing. What's shown here is a little difficult to understand, but let's walk through it carefully. The global mean temperature there on the x-axis, showing today about 15 degrees is the global mean temperature. And if you look at the last glacial maximum, the Ice Age, 20,000 years ago, you can see that the temperature was about 9 degrees Celsius 20,000 years ago on the global average, and that the sea level was about 120 meters lower than it is today. And this is actually quite well understood, because we can see places where the sea level has changed this much. You know, the Bering Land Bridge and places off the coasts that have land, flooded landscapes. So the sea level rose, with 6 degrees of warming, the sea level rose 120 meters in the last 20,000 years. If you look further into the past, 3 million years ago, it was a little warmer than it is today, about maybe 17 degrees Celsius, and the sea level was about 30 meters higher than today. 40 million years ago, there was no ice anywhere on the planet Earth, and it was much warmer, and the sea level was about 70 meters higher than it is today. Yet the IPCC, the UN agency tasked with looking at climate change, forecasts that in this century we're going to have 3 degrees of global warming and virtually no sea level rise whatsoever. What's up with that? Why is that? The reason is it's very slow melting those big ice caps. It takes a long time. If you let the ice melt to the tune of 3 degrees of warming, you get something like 60 meters of sea level rise, not 1 meter as the IPCC predicts. So this is the difference between global warming that lasts for a century and global warming that lasts for millennia. The amount of sea level rise that belongs with a 3 degree warming is enough to put 40% of the world's population underwater. 40% of the population of the Earth lives within 60 meters of sea level. So what do we know for sure? There are things we know and there are things that we're not so sure about. The things we know for sure are that CO2 molecules absorb and emit heat. It's this 3-atom molecule dance thing that I told you about. It's been known for 150 years. There's really no error bar around this. We know this for certain. We know that doubling the number of CO2 molecules adds 4 watts to every square meter of the Earth's surface, kind of in perpetuity, and this has also been known since the 19th century. We know that if China and India industrialize their economies with coal, we won't have just 1 doubling, we'll have 2 doublings in this century. So not 4 watts per square meter, but 8 watts on every square meter. And we know that additional wattage, if you will be maintained for millennia. It's a very sobering set of things that we know for sure. We're not so sure about exactly when and exactly how the climate is going to change in each locality. That's a tough one. It's quite clear that the climate is going to change, and that it's going to change on the order of as much as it did when we came out of the last ice age. That's how much climate change we're looking at. What that does to Calgary or Fort Collins or Singapore, I don't know. It's much more difficult to know locally. The science is easy compared to the economics, the politics, the social consequences. What will people do when the climate changes as much as it did coming out of the last ice age? What will it do to social systems? What should we do about all this? That part is not up to me. That part is not up to scientists. That part is up to everyone. Scientists have, climate scientists in particular, one of the smallest minorities there is. If you sort of do a little thought experiment, think of the smallest minority you can think of. I kind of hesitate to do this, but gay Armenian Republicans for Muhammad. There are more of them than there are climate scientists. And we don't really count in terms of what we as a culture decide to do about this problem. It's everyone's choice. Everyone has to come to grips with this and deal with this over a very long period of time. To put it in a little bit of historical perspective, climate change and CO2 and the carbon cycle and energy will be one of the grand themes of human history over the next millennium. Just as in the last millennium, religious strife and the development of the feudal system and colonialism and the rise of industrial capitalism, those were the big stories in the last millennium. And in the new millennium, our stories, our history, our culture will be defined by these other things, by these physically based changes that are happening to our planet that will transform everything about our lives, about our culture. The worst myth of all is that without the subsidy of the cheap energy that we have now, civilization will crumble, people will freeze in the dark, they'll starve, the sky is falling. I want you to be skeptical of this one. This is a terrible, terrible story that we tell each other that paralyzes us with fear, that keeps us from doing anything about this problem. In order to solve the problem, we have to provide a decent standard of living for all of those billions of people, not just for us. We can't get rid of those billions of people. They're already here. We wouldn't accept a solution that would reduce the population by billions. We have to do this without generating CO2. We have to somehow generate enough energy for all those billions of people that doesn't put the CO2 in the atmosphere, that cranks the thermostat for thousands of years and melts all the ice. From an engineering point of view, this is definitely doable. Okay? If you asked somebody else to come up here, somebody whose background was in electrical power generation or vehicle design or green buildings or whatever, they could tell you the specifics of how this can be done. It's expensive. It's politically difficult. But you're not going to do it by tinkering around the edges. You're not going to be able to do this by riding your bike to work or changing your light bulbs. It requires profound changes in the way we generate energy and use energy in our world. I want you to do a little thought experiment. Our ancestors did something like this. Our ancestors experienced, created the depth of change in their societies that we and our descendants must now create. Imagine it's the year 1800 and you're in charge. I don't know, 1800. Let me see if I remember. Napoleon was storming across Europe. Ben Franklin was playing with keys on kite strings. In the year 1800, imagine that there was some empress of the world and along came a grand vizier with an idea for transforming the world economy. The visionary says, we're going to dig 8 billion tons of carbon out of the ground every year, and we're going to build pipelines and super tankers and railroads, and we're going to transport the stuff to every 7-Eleven street corner on the planet. And cars, we're going to take carriages and stick rubber tires on them and put internal combustion engines in them, and we're going to drive them. Oh, that means we got to build millions and millions of miles worth of paved roads. And electricity, that thing that Ben Franklin does with the kites, we're going to run a wire to every little house and flat everywhere in the world, and people are going to have TVs and iPads and all kinds of stuff to run on the electrical system. And luckily, the Empress has an accountant who's been keeping track of the wish list and says, Your Excellency, we can't afford it. And the accountant would be right. Because if you add up the cost of millions of miles of paved roads and 10 million vehicles a year and all of the houses and all of the electrical system and all that stuff, it was more than the entire wealth of the planet in the year 1800. Where did that money come from? You'd think they must have gone broke in the year 1800 to have created this system that we see today from nothing. How did they do that? Remarkably, it paid for itself. Our ancestors replaced a global economy based on manual labor with the one that we have today. And the cost of the transformation that they experienced consumed every penny in the world. And it also produced every penny in the world. That's kind of how it works, right? If I buy something from you, the dollar changes hands, but it doesn't mean that there's less dollars. The same thing has to happen again. Our descendants have to be as brave and productive and creative as our ancestors were. I ask you to choose your future. There are a lot of people that I know, wise academics, who believe deeply that our modern lifestyle is only possible because we have this cheap fuel, because we have this cheap energy. If you think about this, this is actually a very, very well-established idea in economics, the idea of the multiplier, the economic multiplier. You sort of imagine there's some intrinsic value in a lump of coal that somebody digs out of the ground. And that value comes from the energy in the coal. And somebody sells that energy to somebody else, and then they turn around and they use the money to buy, a house or turn on the cable TV or something like that. So every dollar gets spent 4 or 5 or 6 times. But this extractive view of wealth, of the economy, of human history, has a very dark side that we have to acknowledge. Because what it means is that the whole thing is a house of cards. And when we stop extracting that valuable rock that drives the entire economy, the whole house of cards falls down and everybody winds up freezing in the dark, and we have, population collapse, and we go back to living in the Middle Ages. Gosh, maybe it's right, but I sure hope not. I just can't live like that. I prefer this other story, that our well-being depends on creativity and hard work, that our ancestors actually created this world, and that our kids are creative and smart too, that the society that we live in isn't built on the house of cards of coal. The society that we live in was created by people, and that we're not running out of smart, creative people, and that our future is bright. This gives me hope for the future. It gives me the ability to carry on and face life. It's a brighter future. It's a better future. I want to be an optimist, and I'm going to leave you with that. Thanks for your time.